Because the AP Chem test is set up in a certain way, I'm going to teach you a little bit about some Chapter 16 material at this point. I'm not going to go in depth. This is going to be just a quick overview of some information about entropy and entropy. So this is just some thermodynamics background that we will use now, learn more later in Chapter 16. All right, so the first thing we're going to talk about is entropy, which we learned about in class a little bit. And entropy has the symbol S. And it is a measure of how many microstates a system can have. And we'll discuss microstates a little more in a moment. And there's a very important book note here. You don't need to write the note down, you just need to know. Your book talks about disorder and randomness. And this particular discussion involving entropy, it's not accepted any longer, so you never want to say anything about disorder or randomness when discussing entropy. Rather, entropy is just a measure of how many microstates a system can have. And a microstate is the way in which a particular container could be set up with the particles in it. So a single microstate would be the amount of energy each particle has, where each particle is placed, and how things are arranged within a container. The number of microstates would be how many different ways the particles in a container can be arranged, not just physically, but also energy-wise. So if we think of solids, liquids, and gases, hopefully you recognize in a solid, the particles can't move from one place to another. They're stuck in space. So the entropy of a solid is much smaller than the entropy of a liquid, where the particles are actually capable of moving, so they can move around. There's different ways in which they can be arranged, and there's different energies that they can have. And then the gases have the most entropy because those particles are whizzing around really fast. They can transfer energy from one to another by bumping into each other. So gases have the most entropy when you're comparing the same chemical. Also, actually, if you compare the entropy of gaseous oxygen with solid water, the oxygen gas would have more entropy than the liquid or solid water. All right, one more thing about entropy, S. Entropy has an absolute, not a relative scale, and you should have noticed in some problems that we did, the values for S were given just as S, not delta S. So the value for S is truly 0 for any pure crystalline solid at 0 Kelvin, because the atoms are not moving. They're in their perfect crystalline structure. And so there's only one possible microstate. And the formula for entropy, which we're not going to get into, you'd have to take a graduate statistical thermodynamics class to understand this fully. If there's only one microstate, then entropy is actually 0. So this concept of a relative versus an absolute scale. So here we have the absolute scale for entropy and this relative scale for enthalpy. Entropy has the absolute scale because we know that entropy is 0 at 0 Kelvin for pure crystalline solids. For enthalpy, there's no actual 0. We have to define a certain place as 0. So the relative scale that scientists have decided to use is to say that all pure elements at 25 degrees Celsius in their standard states, have an enthalpy, delta HF, equal to 0. So the enthalpy of formation for pure elements is defined as 0, and all compounds are relative to this scale that's defined by scientists. We could have picked some other relative scale, but we've chosen, we're going to say all pure elements have a heat of formation equal to 0. Then we do experiments reacting elements together to form compounds. We find out what the heat of formation is, And that gives us the heat of formation for the compound because the elements are 0. So we find out how much heat is made when we make a compound, and that's the heat of formation for that compound. All right, so the equation we have for entropy is the change in entropy for a reaction is the sum of the entropy of the products minus the sum of the entropy of the reactants. This looks just like our equation for delta H reaction, but notice right here and right here, there is no delta listed. And that's because of this absolute scale that we have. So we have no delta when we're looking at the products and the reactants for entropy. When we're looking at enthalpy, we would have delta H of formation in the products and the reactants. All right, so Gibbs free energy is a measure of how much work a reaction can perform. So if you're trying to understand, like, what is this free energy stuff? It's not something we measure directly, but it is a thermodynamic quantity that we can use to identify whether a reaction will provide work to make something happen, to power a locomotive, or is delta G the free energy such that the reaction cannot perform any work. And there are many reactions that can perform work and some that cannot. You don't need to worry about that yet. There is an equation that we can use to find delta G for a reaction. And it looks just like what? Yes, hopefully you know. It looks just like delta H, doesn't it? Kind of looks like delta S, but there's something a little bit different here. Oops, sorry about that. Do you notice there are these deltas here? Just like in heats of reaction, enthalpy of reaction, they have the delta H formation. And here we have a delta G formation. So do you think this is a relative or an absolute scale? The absolute scale was the entropy equation. The relative scale was the enthalpy equation. Answers coming up. This is a relative scale. And just like with enthalpy, the Gibbs free energy is defined as 0 for pure elements in their standard state at 25 degrees Celsius. There's another equation that we have for Gibbs free energy. That is delta G is delta H minus T delta S. So if you are given information on free energy of formation of a chemical, you will use the top equation here. Delta G reaction is the Gibbs free energy of the products minus the Gibbs free energy of the reactants. If you have information on enthalpy and entropy, you would use the second equation here, that delta G equals delta H minus T delta S. The temperature, really important. You have to make sure you convert your temperature to Kelvin or you will get the wrong answer. What does the standard state mean? What's our temperature? Hopefully you remember it's 25 degrees Celsius. One other note, let's make a little note there, 25 degrees Celsius. Whenever you see that little 0 there, for thermodynamics, it means 25 degrees Celsius. You have to be very careful with the units for this particular equation because enthalpy is usually given in kilojoules. Entropy, on the other hand, is usually given in joules per Kelvin. Now note, we have the per Kelvin because we have temperature times delta S. So if there was no per Kelvin in the units for delta S, our units wouldn't cancel out appropriately. But what you need to be careful of is one of these has joules, one has kilojoules. You have to make sure you get them in the same either kilojoules or joules unit before you can subtract T delta S from delta H. So typically what students do is they divide the entropy by 1,000 to get kilojoules per Kelvin. All right.